Hello everyone, welcome back to our YouTube channel. I'm going to be briefly taking you through our machine learning project, which is about explainable graph neural networks for heart disease prediction. And I'm Kapma Hamza with my colleagues Namtosi Diana and Kalema Alan, all students of Makerere University. Yeah, so the contents of our presentation include the introduction, the related work, the problem statement, the research questions and objectives, the research contributions, the methodology, the dataset description, the experimental results, the conclusions, limitations and feature works, references, and acknowledgement. So I'll briefly take you through the introduction. So according to World Health Organization, it's estimated that cardiovascular diseases are the leading cause of death globally, taking an estimated number of 17.9 million lives each year. More than 80% of the CVD deaths are due to heart attacks and strokes, and more than 30% of these deaths occur prematurely in people under 70 years of age. This calls for early detection and intervention to reduce the risk of sudden heart failure, improving patient outcomes. Studies find that unhealthy diet, physical inactivity, high body mass index, high blood glucose, and tobacco smoking, which contribute to half of the global burden of heart disease. The related works, there is Tong Chen's work, leverages graph neural networks for heart disease prediction, building on previous research that utilized traditional machine learning approaches. The authors of three in our references developed an interpretable effective AI model for predicting heart strokes, achieving 95% accuracy with techniques like resampling and live explainability. Similarly, Ashishi, Chabi, and team conducted experiments with data from the ACI repository using data mining techniques to predict heart diseases. They employed the K-means algorithm and naive Bayes, finding that adjusting the number of clusters in the K-means algorithm improved the results over the standard setting. Our problem statement is that traditional machine learning models fail to utilize relationships in structured data, whereas graph neural networks effectively capture these connections, improving performance and robustness. The black box nature of GNNs possesses a significant challenge in interpreting and understanding the decisions made by these models. Due to these problems, we seek to implement interpretability of GNNs using SHARP and LINE. So as you can see here, that we're going to have our input, feature extraction, classification, and output according to machine learning. And then according to deep learning, we're going to have our input, the neural networks, and then our output. So our research objectives are to evaluate the performance of GNNs using XAI techniques, to explain individual predictions, to summarize global interpretability of the models, to compare different methods used. As you would see, we're going to use different methods to build different models, to ensure fairness and robustness, to improve model trust and transparency, to provide human understandable explanations. My colleague Namuto Sidana will take on from here to take you through the research contributions.
Hello, my name is Santos Diana, and I'll build on from where my colleague has stopped. So one of our main objectives was implementing explainability for the GNNs to solve the black box nature. So one of our main contributions is being able to implement this explainability, which brings interpretability of the models. And we achieved this using Lime and Sharp. So building on that, I have also improved on the trace and transparent of AI-based models, and specifically here it's this prediction. And then it also, our work has created a benchmark for interpretable GNN models for other researchers who might want to do the same. So from the methodology, first I acquired a data set and processed the data, which we converted some of it to the graph structure for the GNNs. Yes, so and some of this plain data was fed into the traditional machine learning models, and the graph data was fed into the GNN models. And then these results we fed into the XI techniques, which is MIME and SHARP for explainability. And then the overall output is an explainable prediction, which is whether the patient has the disease or not. And it also had this result will come with they explain like all the information, like why this prediction is like, so the different features that contributed to the disease, or if this person doesn't have the disease. So the data set, we got it from URCI repository, and it consists of 12 features, including the target variable. And these are the features of our data set that we used. So here, these graphs just show a sample of the graph data that we got from the data set. This is the graph representation of our data set of different patients and the relationship between them. So for the GNNs, the input is a graph, which I've showed you. And then this data is passed through different neuron layers, and we use a ReLU activation function. And through the different layers, it gives an output. So here on the right is it's an illustration of how message passing occurs and how different nodes interact to come up with a decision to go to the next layer and to the next node, just into like different weights, and basing on that, using this ReLU function to perform the next step. So for the distribution, the EDA visualizations, we have this first one shows the age distribution, and most patients were between the age of 50 and 60. So for the gender, we see that most patients were male, and that's why we opted to use this mode to bring about the dataset balance. And then also for those, this just shows how many patients were having the disease and those that didn't have. So for the heat map here, the lighter the color, it shows that the feature positively correlates to the prediction, and we see that chest pain type and slope, ST slope, and then exercise angina positively contribute to the prediction. So for the results, we performed training on the models, the normal train when you have not applied SMART, and then when we applied the BSMART also. So for the results, they show that the GCN performed better in the GNN. It got a high accuracy than the other GNNs. And then in the traditional machine learning models, is the decision trees that got a higher accuracy than the rest. But as we see from the normal train and well applied SMART and BSMART, we see that there are no really much difference, because this just proved to us that we didn't have a problem of data set imbalance. So we see that for GCN here it had 90, and here on applying SMART it got 89, and just shows also for all the other models, as we can see, either the accuracies remain the same or like they reduce. So that only indicates that our data set was balanced, wasn't having a problem of imbalance. So maybe another thing to note, even when we say that some traditional machine learning models are getting high accuracy, for example, the decision trees is getting a higher accuracy more than GAT, but still we see that the GNNs perform better than traditional machine learning models, in that they give more accurate predictions than the traditional machine learning models. Yes, my colleague will take you from there. Thank you so much.
Hello, this is Kalema Alan, and I'm going to talk about the explainability of the results of the models, as my colleague has mentioned. And in the unexplainability visualizations, we use the force plots, we use summary plots and bar graphs. For the summary plots, as you see here, this represents the feature importance of the model as a whole, and it shows the different features and their importances in order. For instance, we have the ST slope with a sharp value of 0.3, indicating that it's the highest feature. It's the highest feature with the highest feature importance. That means that the model uses this feature. The model uses this feature and others like old peak, and we have we have chest pain and exercise angina. It uses this to come up with a prediction. And for our instances, for certain instances that we were able to test with our model, for example, the 100 instance, we passed it through and it came up with a prediction of 1. We used the force plot to visualize the features that contributed to that prediction. And as we see here, we have the max heart rate, we have the sex, chest pain type, exercise angin, and SS slope. These are the features, and the length of the bars indicate the importance of the features. In other words, the features that contributed highly to that prediction. And down here, this is a bar graph. This bar graph represents the feature importance of the model as a whole. As we saw here, it's the same as the summary plot, because it's same as the summary plot, and the length of the bars indicate the feature importance. So for values, for models that use the technique, the Lime technique of explainability, we use pie plots. And as you see here, the green shows the features the model uses to come up with a positive prediction, and the features that negate that, those are the ones in red. The length of the bars show the importance of the features, as you see. And then for specific instances, these are the visualizations we used, and still they're the same as the others. So in conclusion, we demonstrate the effectiveness of the graph neural networks in prediction of heart disease. By emphasizing explainability, our approach enhances the interpretability of predictions, thereby facilitating clinical decisions and making transparency and trustworthiness. So for future research, we may explore integration of additional clinical variables, application in the field, such as the drug discovery and natural language processing. The limitations while making this project, we had a graph construction. This involved, since our dataset was numerical, we had to change into a graph structure that had to be fed into the models. We also had, not all explainable techniques were working well with models. Some models, like GraphSage, are not working well with the sharp explainability technique, so that became an issue. Feature selection, selecting certain features that really the model had to be used while training to come up with the highest accuracy and also correct prediction. Lack of enough domain knowledge. This was our first project, so we had to learn everything from scratch, and now everything integrates, and it was a challenge. We also had model complexity. As we know, GNN models are a black box. Knowing how they work is really a challenging process. So understanding that and coming up with models that actually do what we want became a problem. For recommendations, we recommend exploring more scalable XAI techniques that are compatible with many architectures, collaborating domain experts and clinicians, using transfer learning for model complexity, hyperparameter tuning, and feature selection, and also distributed parallel computing. For the future works, we are aiming at drug discovery. So these are the references from which we got the work from, and we appreciate Mr. Galiwango for the supervision and support provided throughout the project lifecycle, UCI for providing the dataset and making it open source, and Macquarie University for the resources and the study of machine learning. Thanks for watching.